mistake. So we have Mas Ayu Elita Hafiza and also Michael Manawan and Mr. Sofian Aritonang and Mr. Joko Navalino, a speaker for the lecture about study of oxidation level of inorganic oxidation agent to atom position in solid single base propellant. So is there any Mas Ayu Elita Hafiza? Or the other team is already present?
Yeah, I think I don't see in the participant too, Mr. Radit. Maybe we could continue with the next one.
Oh yeah, okay. Okay, so for the next speaker, we have our contributor from National Research and Innovation Agency, Mr. Joko Hadi Prajitno, with the talk about synthesis, ternary, SNNB and ZRSNNBY, zirc alloy for SMR structural cladding material. So is there new Mr. Joko Hadi already present? For Mr. Joko Hadi.
He is here, Mr. Joko. Yeah.
Yes, maybe Mr. Joko Hadi.
I can contact with, yeah. Maybe because he thought later I can give the.
Yes, because Mas Ayu is not present.
Maybe you can ask the other presenter, the next presenter, and afterwards back to
Yes.
Mr.
Okay.
Hadi. Yeah, the one that present.
Okay. Okay. So apologies for the technical issue, and we can move on to the next presenter or contributor from Republic of Indonesia Defense University Indonesia, Miss Jihan Anavisa, and she will talk about the electronic structure dependence of silicon composition in SEGE alloy, DFT study on meta GGA level. Okay, so Miss Jihan, are you present?
Yes.
Okay, yes. So Miss Jihan, the time is yours.
Okay, thank you for very much for the moderator and for your time. Is my slide? Can you see my slide?
Yes, we can see our slide. Maybe you can have it full.
Okay. Well, first of all, my name is Jihan Anavisa, and currently I'm second year undergraduate student, and I'm from Physics Department of Universitas Pertahanan Republik Indonesia, which is located in Sentul Bogor. And today I would like to present our study. The title is the electronic structure dependence of silicon composition in silicon germanium alloy. adaptive study on GGI. So I will begin by introduction. Well, I think all of us already knew, but the fact that fossil fuel stock is decreasing each passing years and increase of energy demand worldwide is the main right force us to think other ways to fulfill our energy demand. As you can see in this graph, we can see the projection of usage of specified source of energy from 1990 until 2014. So the coal usage is decreasing with the increase of usage of new sources energy known as renewable energy. So one possible source of renewable energy is the solar cell, which analyzes the solar rate to produce the energy required. Other way to reduce the conventional fuel usage to increase the efficiency of energy conversion to obtain from the fuel. For instance, around 30% energy is actually used for movement in a car, while the other 17% energy is lost in the form of heat. So interestingly, that both of these required feature to combat the aforementioned problem is apparent in silicon germanium. So silicon germanium alloy is a very interesting material, which mainly is used in three different technology front. So in the last 4 decades, we can see a significant improvement of silicon solar cell efficiency. However, it kind of reaching its limit in the last 10 years. Now the research focus on how to combine the silicon solar cell with the other material to produce a better solar cells material. For instance, it was known that while silicon atom produce a very good value of band gap, however, the gap characteristic is an indirect one which hinder its efficiency. One of possible solution is to combine with the silicon germanium alloys, which produce a more direct gap characteristic, as the germanium is known to have direct gap characteristic. The silicon germanium alloy is also known for thermoelectric material application, which can produce potential difference or voltage when difference of temperature is applied to the material. So one of the most important feature on this thermoelectric material is the feature of merit, which can be improved by lowering the thermal conductivity, which can be achieved by engineering the crystal structure of silicon germanium alloy, or recently by band engineering. And the last application is the usage of silicon germanium on the transistor technology. While this one is outside of the scope of this research, it is clear that silicon germanium alloy is one of the most important material that is still relevant even to this day. And more study on this system is very encouraging. So a lot of experimental study has been carried out for this system. However, not so much from the theoretical viewpoint specify density functional theory calculation. One of the main hurdle in the fact that germanium is very notorious case in the FT calculation. But common functionals such as LDA and GGA cannot show an insulating band gap. While the more advanced ones such as meta GGA under TB09 formalism shows an inconsistent value of gap energy. Furthermore, it is also known that TB09 requires a predetermined C parameter to correct band gap energy, which produce more uncertainty for the study of germanium system. Thus, in the study, we try to use other meta GCI functional known as ICAMT, or strongly concerned to appropriate norm, which has been successful to open a proper gap for insulating side case. Well, as you can see, the figure on the left, this shows our initial configuration of silicon germanium alloys with the same composition between silicon germanium atom. The dashed line shows the unit structure that is repeated in the C direction to produce 1 by 1 by 2 supercell structure. And this image on the left is silicon 0.5 and germanium 0.5. Then for the next structure, we construct in similar fashion with the previous supercell. However, we reduce the silicon composition by half to produce the silicon 0.25 and germanium 0.75 alloy. So aside from these two configuration, we also include the pure silicon and pure germanium crystal structure. We put all silicon atom in the middle part of supercell to reduce the possible spurious interaction with the next supercell structure. And all calculation in this study will be carried out by using quantum espresso package under the formalism of matrix GF functional scan. We analyze 12 by 12 by 60 points to obtain a proper electronic structure. Finally, we will select all structure until the force between atoms is less than 0.1 electron volt per liter. So this is our first result. That is related that with the structure change measured for the all structure that we calculate in this study. As you can see in this table here, 0 to 1 shows silicon atom composition. In here, 0 defines the pure silicon structure, while 1 defines pure germanium structure. With the reduction of silicon atom, the all structure parameter that is shown on this table is increasing. This is due to the fact that germanium atom is slightly larger compared to the silicon atom. And all structure that is calculated on this study shows a same symmetry with one to the other. Okay, this is next is density of state or dust result. Here we show all the dust image for all structure considered on study. As you can see, the black solid lines show the pure silicon, while the red, blue, and green dashed lines describe the dust image with decreasing silicon content. In this case, the green dashed line shows the dust for pure germanium structure. Okay, so from here we can see that with an increasing silicon content on silicon germanium alloy, the insulating band gap is increasing from 0.5 pure germanium to 0.91 pure silicon. And the gap value for the silicon 0.5 germanium 0.5 alloy is calculated to be 0.89 electron volt. While with the decrease of silicon composition in silicon 0.25 germanium 0.75 alloy is hybrid to 0.75 electron volt. Okay, so all of the affirmation value of band gap value is still lower compared to the real experiment. It's about around 50%. And one possible reason for this that the scan functional is still underestimate the interaction between atoms, which reduce the gap energy. However, it also needs to be mentioned that all of this electronic state is obtained without any external input in the calculation, such as TB09 calculation or the active rescue formalism. Thus, we believe that more studies using the scan functional is required. Okay, so here the summary for our result. By analyzing Nikkei GGS scan functional, we show the reduction effect on structural parameter value with the increase in the silicon content. And all calculations that were conducted on this study show a relatively accurate band gap value, with the error percentage is much lower compared to the result obtained via LGA or GGA functional. Okay, that is all for our presentation. Thank you very much for the moderator and also all the participants in this section.
Okay, thank you, Ms. Jihan, for a great presentation. And if there are any questions from the participant, you can type it in your chat box or you can raise your hand. Okay, if there are no questions from the participant, we can move on to the next speaker. So thank you, Ms. Jihan, for the presentation. And we can go back to the second speaker. So Mr. Rafi, can you please? Okay, so our next presentation is from a National Research and Innovation Agency, BRIN, Indonesia. Mr. Joko Hadi Prajitno, he will present about the synthesis ternary ZRSNNB and ZRSNNBY Z alloy for SMR structural cladding material. So, Mr. Joko Hadi, are you present?
Thanks a lot, Mr. Radit.
Okay.
I want to
Please.
share the presentation.
Okay, yes, the time is yours. You have 15 minutes.
Okay, my presentation deal with material structure for nuclear power plant. So this is not deal with battery, but this is with nuclear power plant. This is the material is used for structure cladding material. I am from a research center for applied nuclear technology, National Research and Innovation Agency. My outline is background, this is focus, experiment, result, and discussion, and finally conclusion. My background deal with development of nuclear power plant. This is the evolution of nuclear power plant. This is generation 1, early prototype of reactor, and this is the second generation commercial power reactor, and this is the third generation advanced light water reactor, and this is also 3 generation plus, and this is 4th generation with main purpose high economical enhanced safety. This is main my research, enhanced safety, minimal waste, and corrosion resistant. The zirconium alloy is used as a cladding material. The position of zirconium alloy is in the core of the reactor. This is the core of the reactor, and this is for a full cladding. Full cladding in this year. This is a temperature until 500 degrees centigrade, and the zirconium 4 is used as cladding material until now, and also this is an advanced zirconium alloy. Advanced zirconium alloy, this is a development of zirconium alloy just only to composition is modified with adding some element to improve mechanical property, chemical property, and technology property. This is my research. Research work just only primarily study synthesis of ternary zirconium stannum niobium and zirconium stannum niobium yttrium alloy. This is my research focus, just preliminary study. experiment. This is the alloy ICAMT sample preparation, cutting and baking, and then I use electric arc melting furnace to melting of the element of the alloy. The melting of the element of zirconium is around 1850 degrees centigrade. So I have capability the electric furnace ini capability until temperature 3000 degree centigrade. After melting, the material is characterized by optical microscope, XRT, and SIM ADS, also hardness of material. This is composition of chemical alloy, set RSNMB by weight percent. This is zirconium, stannum, niobium, and yttrium. And this is added yttrium 1%. This is the element of the alloy. This is zirconium. This is niobium. This is stannum. And then this is I have a single arc melting furnace made by ICAMT. This equipment has capability until 3000 degree centigrade. This is after melting the alloy, and this is the specimen ingot after melting. The button ingot with diameter 20 millimeter and thickness 10 millimeter. After that, the specimen is characterized by optical microscope, SIM ADS, and hardness. This is optical microscope image, the two of the alloy. This is if we look at this is considered of parallel plates and basket with microstructure, and we see more clearly by SEM. This is SEM image, the microstructure of the alloy. This is a parallel plate, and this is a basket width for zirconium, stannum, and niobium. This is 100 micrometer, the magnification, and this is 1000 magnification. And this alloy is added by yttrium. This is the microstructure of the alloy. This is 100 micrometer. This is magnification 1000. So if we look more clearly, this is a parallel plate and basket with microstructure. This is mapping of EDS. Mapping evidence to is used to evaluate the distribution of alloy. If we look at this is a first alloy. Distribution is relatively homogeneous, and this is the composition of the alloy. And this is the second alloy. The distribution of element in the alloy is relatively homogeneous, and this is the composition after EDS analyzed. Is from this here is to get this the composition is relative homogeneous, and the alloy is the same as we planning the composition. This is XRD examination from this figure. This is this alloy consisted of alpha zirconium. This is the main peak of the alloy, and this is some minor peak is beta zirconium. This is the same. The two alloy is not really different. The peak of diffraction, X-ray diffraction is relatively the same, but the peak is relatively big in the alloy with addition of yttrium. In this harness, we use a force with 1 kilogram force and dwell time 15 seconds. It is the harness. We use a 5-time indentation, and the average is in here. This is a zirconium stannum niobium, and this is a zirconium stannum niobium added with yttrium. If you look at this, the addition of yttrium improves the hardness of the alloy. Conclusion, the Microsoft SCAS2 alloy ZR 1% SN, 1% NB, and 1 ZR 1% SN, 1% NB. And yttrium is a basket-based microstructure. Mapping EDS show the distribution element of the alloy is homogeneous. X-ray diffraction show that the pass of the two alloy dominated by alpha pass and minor beta pass. The value of hardness, zirconium stannum niobium and zirconium stannum niobium yttrium are 255 and 277 respectively. Acknowledgement, this work was part of research program of Citaloy development and financially support by the LPDP grant program under contract number 05A13 and PRN 2020 from Research Center for Applied Nuclear and Technology, National Research and Innovation Agency. Thank you, Mr. Adit.
Okay, thank you very much, Mr. Joko, for the great presentation. And for all the participants, if you have any question, you can type your question in the chat box or raise your hand. Okay, if there are no any question from the participant, we can move on to the next speaker. So, Mr. Joko, thank you very much for your presentation.
Thank you, Mr. Adit.
Okay, so we can move on to the next speaker, Mr. Rafi. Okay, so for the next speaker, we have from Republic of Indonesia Defense University, Indonesia, Ms. Mas Ayu Elita Hafiza. She will speak about the study of oxidation level of inorganic oxidation agent to atom position in solid single base propellant. So, Ms. Mas Ayu, are you present? Or maybe Mr. Michael? Okay, I think we'll wait first. Okay, I think we'll wait first. Mr. Rafi for Mas Ayu, because she said that she will be entering the room.
Uh, Mr. Adit, actually, yeah, there is a well technical problem because Mrs. Ayu said, so that in the afternoon session, she has
Okay.
two papers actually, the one here and the other one is in the afternoon. So she
Okay.
asks apology for that.
Okay. Okay. Thank you very much, Prof. Evi, for the information. Okay, so I think we can end this morning session today because all of the speakers already present. And please, all participants, you can kindly fill the attendance list on the chat box. And before we can go to the break time, yeah. Okay, so I'll give back to the MC, Mr. Rafi.
Okay, thank you so much, Mr. Adit, for moderating this session. So before we close, maybe Prof. Evi, are you still here?
Yes.
Okay, so for the certificate to Mr. Adit, could you hand it, Prof? Thank you.
Okay. Thank you for chairing this session, Mr. Adit. Yes, that's given from the NBRI to certificate of appreciation. It's awarded to Dr. Adit, Mr. Adit Triboguna, SA, as Distinguished Moderator in International Conference on Advanced Material Technology on December 14 to 16, 2021. Thank you again.
Yes, thank you very much, bro.
Thank you, Prof. Evi. So now, ladies and gentlemen, thank you also, Mr. Adit, for moderating the session. So, ladies and gentlemen, now we are entering the break session, and we will start again at 1:30 p.m. Thank you very much for attending the session, and I would like to mention also that this event would not be possible without our sponsor, IUMRS, MRS INA, MRS Thailand, PT Surveyor Indonesia, and also supported by Queen Mary University London, AONSA, INSS, and INVN. So So thank you very much for our sponsors and supporters. And once again, ladies and gentlemen, don't miss out on the afternoon parallel and plenary session, and have a pleasant break. Thank you. You may leave the room.
Thank you, Raffi.
Thank you, Prof. Evi, Mr. Radit, and all the presenters.
Thank you, Mr. Raffi.